Welcome to iTTV for Form 4 Chemistry. Today's lesson, explaining changes of state. In our lower secondary, we learned about changes of state. We learned that solids can change into liquids, which we call melting. Liquids can then change into gas, which we call boiling. We can also go the other way. A gas can become a liquid, which we call condensation. And a liquid can change into a solid, which we call freezing. And then there was that weird one where from solid we could go straight to gas, which we called sublimation. Today we're going to investigate and have a closer look at changes of state. Now in chemistry, changes of state are very important for two things. One, we like to change the state of matter or a substance or a chemical because it might help us make a reaction occur faster, or it might help the material be used in a better or more effective way. Also, change of state is very important because it is directly linked to kinetic theory. In kinetic theory, the third statement is very important with today's lesson. As the temperature increases, the kinetic energy of particles increase. Now, this is really what we are going to link to changes of state. Because when we change the state of something, we heat it up and the kinetic energy increases, or we cool it down and the kinetic energy decreases. When the kinetic energy changes, the particles, their arrangements also are going to change accordingly. So let's begin by having a look at some of the key things that we need to remember. Changes of states is caused by heating or cooling. Now, when we studied the change of state of water, we learned that when water boils or when water melts, which is ice melting into water, the temperature remained constant. That means that when ice, which is a solid, changed into water, which is a liquid, at what is known as the melting point, which is 0 degrees Celsius, the temperature actually never changed until all the solid ice had changed into liquid water. I know this is a bit hard to believe because you are heating something up, and as you're heating it up, the temperature doesn't go up anymore. Proof is in the eye of the beholder. So to prove to you that the temperature is constant during a change of state, we need to do an experiment so that you can actually see the thermometer not changing while the heat is still being put into the matter. A heating curve. Temperature constant during change of state. Now, you saw the experiment that we did in the laboratory, and you saw quite clearly with your own eyes that as the ice started to melt and as the water started to boil, in both those cases, the temperature remained constant while the change of state was occurring. Also, you saw with naphthalene, when we heated up the solid naphthalene, as it changed into liquid, the temperature remained constant at 79 or 80 degrees roughly until all the solid naphthalene had changed into liquid. What this gives us is what we call a heating curve. From the data we collected, we can actually draw a heating curve. Let's sketch one up here. So this is what we call a heating curve. Sorry, my R's are always a bit weird. A heating curve. So we draw this graph. On our X scale, we'll put in time. which could either be in seconds or in minutes. Okay, so we'll leave that out there. And up here on the y-axis was our degrees Celsius. Now we'll just keep it simple, we won't put any values in here. But what we got was the temperature was rising, and then suddenly the temperature stopped rising, and we get this flat line. Now it's during this flat line that the change of state was occurring. When ice is melting, the temperature remains at 0 degrees Celsius. When water is boiling, the temperature remains at 100 degrees Celsius until all the water changes to steam. And with the naphthalene, it stayed at that level until all the naphthalene had melted. Once it had all melted, the graph started to rise again. So this is what we call a heating curve. In this case, we are saying that we started with solid and we went from solid all the way to liquid up here. What is important to know is that during this point here, where we are changing state, which in this case is called the melting point. If you dot a line back here, this temperature here will give you your melting point. During this state here, where we are at the melting point and we are changing from solid to liquid, please understand we have both solid and liquid in this area here. Both solid and liquid are present. Of course, at the beginning here, there'll be more solid, less liquid. And by the time we get closer to the end of the melting process, there'll be more liquid, less solid. Bit of common sense needed here. So this is what we call a heating curve. But what about if we go in the opposite direction? A cooling curve. Temperature constant during change of state. Now, in a cooling curve, once again, we are showing how something is changing as the heat is being released. Let's sketch this on the board as well. This is called a cooling curve. Now, in a cooling curve, we still have the two axes, just as just now. This axis will once again be time. Same as just now, can be in minutes or in seconds, depending on which one we're doing. And up here, degrees Celsius. So, as we cool something, the temperature is obviously coming down. Temperature is not going up. So our temperature starts to drop. And then suddenly we get our flat line where the temperature is constant. This is when the change of state is occurring. It changes and it changes and it changes, and when the whole change is complete, the temperature starts to fall once again. If we were cooling a liquid, over here, liquid. Liquid cools and becomes a solid. The temperature at which a liquid changes to a solid, here, this is your freezing point. So here we are freezing. And in this area here, where the line shows a constant temperature, we must have both states. In here, we have both liquid and solid present. Bit of common sense once again, everyone. More liquid here, more solid at this area over here. So this is called the heating curve, and this is called the cooling curve. And we can plot these graphs based on the information we collected when we were in the lab. A few points to remember. Melting and boiling, heat is absorbed. Condensation and freezing, heat is released. Now here we are really looking at some core basic material back to our kinetic energy. As the temperature increases, kinetic energy increases. So when we are heating something up, the melting process and the boiling process, in both those cases, as your curve starts to go up, your kinetic energy is increasing. Your particles are moving faster and faster. In a cooling curve, the temperature is coming down, which means the kinetic energy is decreasing. It means the particles are moving slower and slower. Basic kinetic theory. As your temperature rises, the kinetic energy increases. As your temperature falls, your kinetic energy decreases. Try to remember this because it's really, really essential. States of matter. Remember, particles gain kinetic energy as the temperature rises. Now, one of the key things that we question you on, one of the key things that we need to know that you understand is to know whether you, the student, are able to explain to us how these changes occur as we heat something up or we cool something down. You've got to be able to explain the changes that occur. When we talk about changes, we're talking about the basic changes of solids, liquids and gases. We're talking about, number one, arrangement. Number two, kinetic energy. And finally, the other thing that we need to also discuss is the force of attraction. These three things, you must be able to explain how the arrangement changes as the temperature rises, how the arrangement changes when the temperature is constant and the change of state is happening, how the arrangement changes as the liquid starts to be heated. What about a cooling curve? Same thing. We want to know how the arrangement is changing as we keep coming down. We also want to know about the kinetic energy. How is that changing as we come down? What about the forces of attraction? Are they increasing? Are they becoming stronger? Are they becoming weaker as we cool something down or as we heat something up? You've got to be able to explain. Remember, explain means tell us what is happening, what is changing. And we are always talking about these three: arrangement, kinetic energy, force of attraction. Those are your three things that you've got to be able to explain in a heating or a cooling curve. Explaining the heating and cooling curves using kinetic theory. Key points of heating. Heat is absorbed, gain kinetic energy, vibrate faster, particles move further apart. So let's go over here to the board. This is the first part that we are talking about. We're over here in a heating curve. We're heating up a solid and we're trying to make it into a liquid. What we need to be able to explain in terms of arrangement, kinetic theory and forces of attraction. We start by saying heat is being absorbed, which means kinetic energy is increasing. If the kinetic energy is increasing, the particles are moving faster. If they move faster, let's go to the arrangement. They start to move further apart. They're moving further apart. If they move further apart, how does that relate to force of attraction? Force of attraction is becoming slightly weaker. So this is how we explain it. Now let's go back to the slide. Second part. Heat energy absorbed is used, okay? Heat energy absorbed, used to overcome forces of attraction. Now, if we go back to the graph that we have here on the board, what we're talking about is this area here, which is the change of state area. Now, the temperature isn't changing. Because the temperature isn't changing, we don't speak about kinetic energy. Kinetic energy is directly related to temperature changes. If the temperature doesn't change, the kinetic energy isn't changing. What is happening here is our particles are moving further apart. That solid structure is changing into liquid. Particles that had a fixed position and vibrated only now move out of their position and start to move slowly. What happens here? Heat absorbed is used to overcome forces of attraction until solid changes to liquid. Once we've reached this point, now we need to start dealing with this area here. So let's go back to the slide. No orderly arrangement. Particles move faster, particles move further apart. So if we come back here to the board, this is the area now that we're talking about. Area number 3. Once again, relate your answer to arrangement, kinetic energy, and forces of attraction. We're in a liquid state. The particles are not orderly, but closely packed. Remember, clos packed orange. Okay, bit of French there. Clos packed orange. Closely packed, but not orderly. Temperatures going up, kinetic energy increasing. If your particles are moving faster, they move further apart. Force of attraction becomes weaker. So remember, when you are explaining a change of state, you must be able to explain everything from one state leading to the next state. You've got to explain what happens as the temperature goes up. Explain what happens when the change of state occurs. Explain what happens in the new state as temperature increases. And keep your answers clearly linked to arrangement, kinetic energy, and force of attraction. Key points of cooling. At the beginning, heat is released. Lose kinetic energy. Move slower. Particles move closer. During the change of state, heat loss to the surrounding is balanced by the heat liberated as force of attraction becomes stronger. In the solid state, orderly arrangement, kinetic energy decreases. Particles vibrate slower. So once again, if we jump back here to the board, they can also ask you to explain a cooling curve. Remember, you've got to explain everything in each of the 3 areas. Area 1, your kinetic energy is becoming less, you move slower, your particles move closer together, your forces of attraction are becoming stronger because you're coming closer. Force of attraction is about how close you are. Close, very strong force of attraction. Far, weaker forces. Then your cooling area here. This is the change of state. What is occurring here? Here, energy released is balanced by energy liberated as the forces of attraction become stronger. Once your change of state has finished and we cool the solid down, kinetic energy decreases. Particles go back into a nice orderly arrangement, closely packed, vibrate slower. Forces of attraction become even stronger. So remember, you've got to be able to explain a heating curve and a cooling curve, and clearly when you explain it, do it in a disciplined way. Talk about the arrangement, talk about the kinetic energy, talk about the forces of attraction. Don't leave any of these out. Each one in an examination gives you marks. Question. Describe the changes that occur when ice turns into water. Your description should include changes in arrangement, forces of attraction, and kinetic energy. So this is pretty much what we've just done. This is a typical examination question. They want to know, does the student know how to explain the changes that occur when heat is absorbed, when the temperature is rising? Is the student able to explain what is occurring during a change of state when the temperature is constant? Can the student further explain what occurs in terms of energy and arrangement as the temperature of the new state increases? So this is what they want to know. This is what we want to test. We want to see if you understand all of these. So let's look at the answer. Firstly, when the solid is heated, heat absorbed, gain kinetic energy, vibrate faster, particles move apart. When the temperature is constant, heat energy absorbed used to overcome forces of attraction. In the liquid phase, no orderly arrangement. Particles move faster. Particles move apart. Now, please understand that what we've done here is given you the key points. You need to make these into proper sentences. For example, when the heat is absorbed, particles gain kinetic energy. Full stop. The particles begin to vibrate faster. Full stop. Particles move apart. And then remember, we have to relate it to forces of attraction. Forces of attraction start to become weaker. And then when you're doing the area where the temperature is constant, say when the temperature is constant during the melting point or the boiling point, heat energy absorbed is used to overcome forces of attraction. And then tell them, until the solid changes to liquid. So make your sentences more complete. It's a question of practice, practice, and practice. The more you practice writing these answers out, the more you get into your system that the answers are simple, they are factual, and they have an orderly arrangement, just like solids. We talk about arrangement, we talk about kinetic energy, we talk about force of attraction. We talk about part A of the graph, we talk about part B of the graph, we talk about part C of the graph. Don't leave out anything, and don't write material that is not related to what we are investigating or what we want to explain. Let's try another question. Why is the temperature constant between 10 and 18 minutes in the graph below? So if you look at the graph, 10 and 18 minutes, the temperature is constant. This appears to be a change of state area of the graph. So this is a heating curve, and your answer is always going to be the same. So refer back to the heating curves from the earlier slides and look at what we wrote down during that moment. Let's have a look at what the answer should be. Heat energy absorbed used to overcome forces of attraction. So remember over here, when we are at a constant state in a heating curve, always heat absorbed is used to overcome forces of attraction. Even if we go further up into the gas phase up here. And in a cooling curve, whatever it is, whether it's liquid to solid or gas to liquid, heat released is balanced by heat liberated as forces of attraction become stronger. These two always you're going to be tested on, okay? Because we want to know that you understand what is occurring during a change of state. So remember, change of state, we're changing from solid to liquid to gas. You need to be able to explain what occurs as the temperature rises. You need to be able to explain what happens when the temperature is constant. And you need to be able to explain what happens as the temperature falls. Keep your explanations connected to arrangement of particles, kinetic energy, and forces of attraction. That's all the time we have for in today's lesson. Thank you very much for watching ITTV.